Welcome to my Introduction to Networking course, typically abbreviated ITN. This will be for the CCNA version 7 curriculum. Welcome to Module 11, IPv4 addressing. So in this module, we're looking at the structure, we're going to be looking at the characteristics, we're going to be looking at the types of addresses, we're going to be talking about network segmentation via subnets, and we're going to be talking about how to do basic subnetting on a IPv4 network. So those are the 5 main sections, so let's jump right on in. Section 1, IP4 addressing structure. First of all, there are 32 bits in a IPv4 address. The bits are broken up into 4 groups of 8. Each group of 8 is called an octet. Basically, what we look at when we're looking at an address is we're looking at what sections belong to which group. And what I mean by group, it could also be construed as portion. What belongs to the network and what belongs to the host. Portions of the network we don't get to touch. We only can manipulate the host portion. That's what we assign to hosts. And we actually do the segmentation by looking at a subnet. And a subnet is also a 32-bit stream of binary numbers, also broken up into 4 groups of 8. Subnets will always be either straight ones to a point, and from that point there'll be zeros. You will not find intermingles of ones and zeros. It will be a string of ones, then a string of zeros. Now, the different bit placements can actually range, so it can be 29 ones and 3 zeros, or it can be 24 ones and 8 zeros. Again, there are 32 bits in the addressing scheme, so it's always going to equal up to 32. So you take how many ones there are, take how many zeros there are, and that total number will be 32. So the next portion is, how do we figure out the networking portion when we're looking at a subnet? If we line the subnet underneath the IPv4 address, where the ones are in the subnet mask, that dictate the network portion. Here we have the network portion ending on a boundary level. It ends after the 3rd octet, the 3rd group of 8s. That means the entire 4th octet is the host portion. Well, this is how most default routers are set up, but this is not how networking is generally structured. We normally have different prefix lengths, or we have different subnets. So in this format that we're looking at now, it's called dotted decimal form. 8 bits, and it will be dot 8 bits dot 8 bits. That's dotted binary. Dotted decimal will be the decimal representation separated by dots. Again, 4 groups. Each group can be between 0 and 255 decimal number. Why between 0 and 255? That is because if you take 8 bits and you turn them all on, the largest number it can be is 255. The smallest number, if there are no bits turned on, would be 0. That is why each group will be between 0 and 255. Prefix length that we already talked about, subnet length, will be a string of ones to a point, and then once it gets to a 0, the remainder will be 0. I'm going to grab my pen. So this is the boundary for the network and host. This is the boundary for the network and host. Again, wherever the last one is, that is the boundary between network and host. These are all on a boundary level. First octet between the first and second. Here we're looking at the second between second and third. Here we're looking between the third and the fourth. This guy right here happens to be in the fourth octet. He's not on the boundary, but that is the host, sorry, 0 is the host. This is the network portion, even though it's not on that dot boundary. And again, as we go down further, all of these are starting to get into deeper in the fourth octets. This is called slash notation. /8, /16, /25. That just means there are 25 ones out of the 32 bits. So again, we break this down from the far left, and we count all the ones, and then we group them into groups of 8. So here we have /27. We have 27 ones. Starting from the far left, we count back 8, put a dot. Count back 8, put a dot. Count back 8, put a dot. And the remaining 3 bits are in the fourth octet. And that's just using the /27 as an example. So, now that we have that part taken care of, when we discussed in a previous chapter our binary conversions to decimal, remember that these are positional. This is the 1 position, then the 2 position, 1, 2, 4, 8, 16 position. Then we have the 32 position, then we have a 64 position, then we have a 128 position. The positions matter, and we're going to get into that in 2 slides when we talk about counting our hosts. So, again, in this lecture, we're looking at the Cisco textbook way of subnetting. They like to do what's called ANDing. And essentially, where you look at the IP address and you look at the subnet, if there are matching ones, 1 and 1, it will equal 1. Everything else equals 0. And so you'll do that, and you will find the network address, or you will find the network portion, depending on how you want to look at it. Realistically, I like to think of where the ones are, that's what you can't change, so that's what you carry down. Here, 1 on 1 equals 1, 1 on 1 equals 1, and you just keep going down the list. Or, these 3 octets are all 1s, so that is the network portion. We just keep these. We don't get to manipulate them. We don't manipulate them because the subnets lock them in with the 1s. In our core shell lecture, there is a video looking at things like a broadcast, a network, and things of that nature. So again, when we are trying to build this up, we have 3 main categories. We have our network ID, we have our hosts, and we have our broadcasts. And the sad part is this slide just doesn't quite do it justice. So the network addressing is going to be what we provide for the overall network. That's going to be the main network address. That will give us a way to reference that entire network. That's the first address. The first usable address is typically 1 above the network address. The last usable address is known as the broadcast, and that's going to be where the host portion is all 1s. The last usable address is going to be 1 less than the broadcast. So essentially, when we look at this, if you're looking at the network portion, and you know what's the network and what's the host with all 0s, that's the network address. The network with that has the host portion as all 1s, that's the broadcast. Everything in the middle is what's known as the usable range. and that's where we get the first usable and last usable. Now keep in mind, this is a range. So the first usable might be 1. The second usable might be 2, 3, 4, 5, and so forth until we get to the last address. It's not just 2 addresses, it's a range of addresses. So let's go ahead and jump in. Let's talk about address types. There are 3 main characteristics of addresses that we have to discuss: unicast, broadcast, and multicast. So jumping right on in, unicast. It will go from a single source to a single destination. A broadcast goes from a single source to every destination. Basically, the switch will receive a broadcast and forward it out all ports except the receiving port. A multicast is going to be one unicast for the source to a group of destination. Not all destination, but just a select group. The group could be all laptops, all Dell computers, all HP servers, all routers running a specific protocol. That is what multicast does, one to a group. So let's go ahead and talk about types of addresses. There's a few different types of special addresses used within IPv4. Typically, the first one that has to be discussed are things called private IP addresses. These are addresses that are not allowed on the internet. They are different than a public address. Public addresses are globally routed on the internet or between ISPs. Private addresses are ranges of addresses that are kept so that they cannot be used on the internet. What ends up happening is, at like a small home, you will have a private address. For your home to get on the internet, there has to be something that will mask your private address to an ISP's public address. Your ISP provides one public address for your internet provider, or for your internet, whether it be a cable modem, a DSL, or whatever. What ends up happening is you may have 20 or 30 devices. You don't get 30 public IPs. You get one, and everything uses that single address. At home, your private addresses will either be one of 3 ranges of addresses. It will either be in the 10 network. Anything starting with 10 is a private IP address. For the second range of private addresses are going to be 172.16. This is going to be anything that starts with 172.16 through 172.31. Again, those are going to be the first and second octet. Those are all private addresses. Lastly, anything that starts with 192.168 are also private addresses. Again, these are not routed on the internet, so I can have a 192.168 address and you can have a 192.168 address, and it's fine. These are not allowed on the internet. Again, there's a masking that takes place that will mask these private addresses to an address that's allowed on the internet. So the masking technique is known as NAT, Network Address Translation. This is what translates an IPv4 address to a public IPv4 address. All right, moving on, we have a special type of IPv4 address known as a loopback address. This is basically a way to test the TCP/IP stack or operations of your device. It basically says ping yourself or loop back to yourself to verify functionality. We also have a link local address. If there is no way to obtain an IP address, manual configuration did not take place, and there's no DHCP server that's able to be contacted, what do we do? Well, a link local address will be automatically assigned. They're also known as a PIPA address, an automatic private IP addressing address. This is also sometimes referred to as a self-assigned address that is automatically given to you after a given time of no address. So there used to be these things called classful addresses. Class A, Class B, Class C, and other. These had a fixed subnet length, or a fixed prefix. So Class A was between 0 and 127 in the first octet. You'll notice that the private 10 address falls in Class A. Class B was anything between 128 and 191. Again, in the first octet, this was a Class B. You'll notice that 172.16 fell in this class. Class C happens to be anything that starts with 192 and goes through 223 in the first octet. This is Class C. You'll notice the third private address range is 192.168. So each of these classes have a private address range. We don't do classful addressing anymore. We do classless, meaning we are not tied to the fixed length that are in these classes. A common question I get is who assigns IP addresses? There are different groups. IANA for America. We have LACLink for Latin America. We have AFRINIC for Africa. We have APNIC for the Asian Pacific, and we have RIPE for Europe and most of Middle East and Upper Russia. These organizations control our addressing. The groups are called Regional Internet Registries. They are all managed by IANA, and that is the Internet Assigning Number Authority. This is the group that assigns which of these countries or which of these group of countries get what addresses. So let's go ahead and move on to our next section, which is all about network segmentation. We have what's called a broadcast domain. A broadcast domain is a layer 2 domain that can be forwarded. So essentially, if we have one switch and they send a broadcast, it goes to all switches. It will go out every interface except the port they received it on. It will not cross a layer 3 boundary. Things like ARP and DHCP use broadcasts to propagate information. Well, the propagate requests for information. Again, broadcasts do not cross a layer 3 boundary. So what we can do is we can have a large network. Well, the problem is the larger the network, the more broadcasts. The more broadcasts, the more resources that are used. The more resources, the slower the network operates. So what we can do is we can actually separate the networks. Instead of having one large network, we may have two smaller networks. And again, they do not cross a layer 3 boundary. So the above photo of 400 users on one network, and you'll notice the diagram underneath it, which is two networks, each with 200 users. The 200 users will not affect one another because broadcasts do not cross that layer 3 boundary. This is a way to segment the network. This is physical segmentation. So you'll see that each network is a physical segmentation. But in reality, we don't do this physically. Again, the purpose is so that we can reduce the overall network traffic, we can improve performance, we can improve security, we can actually look at traffic behavior, things of that nature. We can group things like by location or group or functionality or by device types. We may have all printers on one network, all servers on another network, all phones on a third network, all computers on a fourth network. The problem is this is not done through physical segmentation. In the next class, the next course, not in this course, we will talk about virtual segmentation, virtual LANs, called a VLAN. That is where we actually dive deeper into this segmentation conversation, because realistically we will not have dedicated physical segmentation. It becomes very cumbersome. So let's jump into our last session, and this is going to be subnetting an IPv4 network. We already discussed subnetting on a boundary, on an octal boundary. So that's going to be after the first 8 or after the first 16 or after the first 24. That is the boundary. We already know that we can do that. Essentially, what ends up happening is if we are doing the diagram chart on the bottom left, we have networks of a /16. That means for each network, the first 2 octets of the network are not going to change. And you'll see that here. They start with 10.0. The entire network, usable, and the broadcast all start with the same network ID, or the network portion of the network ID. And each of these are different networks. So this is the first network, third network, fourth network, fifth network, and so forth. Here we do the exact same thing, except we're locking in the first 3 octets. And so those match. And so forth. First network, second network, third network, and so forth. Oh, so right here is a special case. When we can go higher, no more, what happens? We can actually increase, since 255 is the largest number, just like when you're counting pennies and you get to 100 pennies, you actually can move decimal places. This cannot go any higher, so you can increase the second octet now. That's why the next network is 10.1. And we can keep going, and then we'll have the second octet go to .2, then .3, and .4. This allows us to have 65,000 possible subnets. Essentially what we do is we look at how many of the host bits there are, and from there we can figure out how many possible subnets. And each subnet will have a host range of 254 possible addresses. So here we have our boundaries that are not attached to a specific octet. So here we have the number of subnets. What we can do is the number of subnets you can look at is the position of how many ones there are. So with this /25, we have 1 in the 4th octet. 1 to the power of 2 is 2. Here we have 2 bits. So 2 to the power of 2 is 4. Here we have 3 bits. 3 to the power of 2 is 8. And so forth. That's how we get to how many number of subnets. How we can quickly get the number of hosts is we can look at where the last one is. That's in the 128 spot. We subtract 2. 1 for the network ID, 1 for the broadcast. That provides us 126 usable addresses. Here, the last one is in the 62 position. Here, the last one is in the 32 position. Here is the 16 position. Here is the 16. Here is the 8 position. Here is the 4 position. Again, all we're doing is we're looking at the last one, subtracting 2. That's how we get our host counts. In our lecture, we have videos that are in the reading. We also have a packet tracer defining our subnetting scheme. One of the last things we have to discuss is subnetting on a /16 and a /8. So we have to look at the different groups. Again, same thing as we discussed before, but why are the number of hosts so much larger now? Look at how many zeros there are. You can do this based off of the 1 or how many zeros there are. So in this example, we have a /16 as the overall summary address, meaning we have one large network with a /16. We can take that one address and we can group it into larger chunks. Or we can break it up more. So you see we can have a /17, 18, 19, 20, and so forth. You'll notice within the /16, all of the groups in the first and second octet do not change. Only the third, even though the third, we're manipulating the third network bits, that is because we're creating subnets with a /16 prefix. This actually is explained way worse than it really needs to be. What we do is essentially we look at where the network bits are and we build off of that. If we're trying to summarize addresses, that's different, and this chart really doesn't do it well, or doesn't really do it justice. So how do we get the number of hosts? Well, this is the 128 position, and normally we could restart, or we can just keep doubling. This is the 256 position, 512 position, 1024, 2096, 4000 something, 8000, and so forth. This is the 32,000th position, 32,768. Subtract 2. That's how we get the number of hosts. This is the 16,384 position. Again, start with the far right. Start with 1, just double. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and it just keeps doubling. And that explains how we get the number of hosts for all of these networks. This right here is in the 1024 position. Subtract 2, that's how we get the total hosts. Again, what we're doing is when we're doing the calculation, we're just starting with 1 and we just keep doubling. We're talking host counts here. So we don't actually have to restart from 1 when we cross that boundary. We can just keep doubling because we're dealing with the host bits. We're counting how many hosts there are. So if we're looking at 100 subnets with a /16, this is called bit borrowing. Basically, the figure will display the number of subnets that can be created when you borrow bits from the third and the fourth octet. If you're borrowing 1 bit or 2 bits or 4 bits or 5 bits and so forth. To satisfy the requirements of 100 subnets for the enterprise, we could borrow 7 bits. And that means we're going to be dealing with that 7 is going to be there. That's going to give us 100 different networks. Realistically, I've never done addressing schemes based off of how many networks. I've looked at how many hosts, and we build off how many hosts. If we're dealing with a /8 for some reason, you could do the exact same thing to figure out how many hosts you need to borrow, or how many bits you need to borrow from each of the octets. we have a lab discussing this. 11.7 is subnets to meet requirements. This is going to be looking at subnetting to figure out how many addresses. So here we're looking at subnetting private versus public IP4 address spaces. Again, private addresses are going to use the 10.172.16 or 192.168 boundaries. And here we can have an internal network using a private address. We can have a DMZ that is either public or private, but using NAT to actually NAT our address space. So we can have an internal private address for our DMZ that is NATed to a public address. Here we have figuring out how many addresses we need, how many subnets we need. Here we're looking at if we're dealing with two private addresses networks, we're going to need two different subnets. But that's the thing is, we need to also understand how many devices per subnet. If we have to have one subnet that is capable of handling 500 hosts, and we need a DMZ that can handle 10 hosts, they're not going to be the same size subnet with host count. So /25 doesn't work here. But again, the number of hosts is what we give to our devices. That's usable hosts. The number of subnets are basically the individual groups that we're going to need. In this example, we're talking about efficient subnetting. Essentially, if we know how many hosts we need, we can group them accordingly. This will allocate, this example, we are looking at 10 host bits. That means we can get 10 subnets with a /26. Problem with the /26 is, does that give us the addresses that we need? And we already know it won't. If we have a /26, we're getting less than 30 hosts per network. So it kind of just depends on how many hosts are we trying to get. How we figure out the host count is essentially we look at the last one position, and that gives us a grouping size. And that actually I'm going to save for a different lecture because we need to here just look at the host count. If we're looking at our host count here, this is going to be total hosts. This is not a /26. This is actually a /22. We get our 1,024 addresses minus the 2 for our usable. So again, here this is going to allocate 10 networks, but each network is not going to be 1,000 hosts. If we need 1,000 hosts, we're going to need a /22. So you have to keep in mind when you're doing the calculations, how many addresses do you need? How many networks do you need? Those two pieces of information allow you to calculate how many networks and how many hosts. We get the /26 because we really do not need that many public addresses. In this example down here, we're dealing in the less than 62 hosts per network. That's that /26 gives us just under 64 usable hosts. So that's why we have 40 public, 25 public, 15 public, 10 public, 30 public. All of them fall underneath that total host count per network. /26 gives us 62 usable hosts per network. We have another lab verifying that you can do this. And this is where we get into the meat of our addressing. That is called Variable Length Subnet Masks, VLSM. VLSM basically means that we can change our subnet mask accordingly. Here we have 4 buildings. They all have the same subnet mask. The hosts between each building has the same subnet mask. Well, this is inefficient. This is wasteful. With VLSM, we can actually modify this so that we don't need to waste so many addresses. Here, we are wasting 28 addresses per network. So we have a lot of waste. What we can do is, between each host, between each building, maybe instead of a /27, we only need 2 usable hosts, we can apply a /30. /30 gives us 2 usable hosts. That means we are wasting addresses. We can also then tighten the different buildings so that we're not wasting addresses again. But in this example, we're looking at just the interconnections between the buildings. Here, again, using VLSM, we're going to subnet the LAN so that we have a little bit better structure. With 25 hosts, with 15 hosts, with 28 hosts, they all fall underneath our 30 usable host range. So all of them would be appropriate because we either have 126 usable hosts. Again, I'm staying in the 4th octet. We have 62, up to 62 usable hosts. We have 30 usable hosts. And underneath 30 usable hosts, we have 14 usable hosts. Then we have 6 usable hosts. Because again, if we're looking at the binary, we have 1, 2, 4, 8, 16, 32, 64, and 128. Again, we're subtracting 2, that gives us our usable count. So 126, 62, 30, 14, 6, and 2. This is our /30, so that's why we get our /30s for these interconnects. For building A, B, C, and D, they are greater than 14 hosts, so that network doesn't work. We've got to be in the network that gives us 30 usable addresses. Yeah, we're still wasting addresses in each group, but our waste is less. So what is the structure and design aspect of our subnetting? Essentially, a network has to be able to grow. It needs to be able to expand as the network expands. So to develop an IPv4 network, to have an appropriate addressing scheme, you need to know how many subnets there are now and how many may be needed in the future so that we can build on a growth. How many addresses are going to be private, how many addresses are going to be public, and what information is going to be needed. Basically, you can examine the needs of an organization to determine the subnets and the overall host counts. If we're doing this in a structured fashion, we'd be performing a network audit. You'd be looking at network requirements, looking at the entire network, how we're going to organize it, how we're going to group it, how are we going to add DHCP for address assignment to each of the groups, and how many hosts per segment. So we also have to look at how are we going to be doing our addressing. That's typically going to be done through DHCP, but we can do end user clients using DHCP. We can have servers and peripherals. Maybe these are static addresses. Maybe these are DHCP with reservation addresses in DHCP, so they always get the same address. If you're dealing with servers that are accessible on the internet, maybe we assign them a public IPv4 address, or maybe we assign them a private address statically and we map NATing to them. We have to make sure that we have intermediary management security devices that allow our devices to communicate. All of these have to go into our network planning. We have a lab discussing packet tracer and VLSM design. I've done several videos on VLSM and the importance. If you're going into networking, you need to understand VLSM and how it functions. If you want links to any of those videos, leave a comment and I will get those to you. That is the end of this module. We talked about VLSM. This is one of the labs you're going to be doing. You're going to be doing a lab design on VLSM schemes. Again, examining the requirement and then designing the lab. In this overall module, we looked at subnetting on boundaries. We talked about private addresses. We talked about public addresses, who organizes them. We talked about network characteristics like broadcasts, unicasts, and multicasts. We wrapped it up with VLSM and kind of the importance and kind of what you'd be assigning to certain types of devices, either statically or dynamically. And that is it for this lesson or this module. If you have any questions, please reach out. Thank you.